Of course, yeah, of course. In fact, it happens on this problem for a different critical point.
Where D is greater than 0 and f double x is 0 as well.
Oh, I see. Yeah, of course. Yes, that's happened before, huh?
But there's no formula for that.
No, because there's a minus sign. Wait, oh, I see. If fxx, and let me catch up to you. I understand what you're saying now. If fxx is 0, d is going to be less than 0 or equal to 0. There's no way it can be greater than 0. So what my brain was hearing you say was something related to like the second piece of the d, not the d itself. All right? There's no way. If fxx is 0, right? Because it's fxx squared, fyy squared, minus fxy squared. Or no, it's not squared. If this is 0, there's no way in hell d could be positive, is there? There's no way. How would it become positive when it's 0 minus a positive number? No way it could become positive. I like it. So I wasn't hearing you correctly. I thought you were talking about this second piece, b greater than 0. That could happen all day long, right? That would be, d would be less than 0. That would be a saddle point, right? Yeah.
So is there ever a time where overall the ending statement comes out to d equaling 0?
Oh, hell yes. It happens on this problem. So what critical points you guys get for number 2?
2, 1, negative 2, 1, 0, 0.
All right, let's catch up here. Yeah, that's what I got. So on number 2, you should get 0, 0, 2, 1, and negative 2, 1. I like it. And fxx was 2 minus 2y, fyy 4. So if you do this one, what do you get? You plug a negative 2 up there for fxx, so it's fxx, fyy, minus fxy squared. Yeah, negative 2 plugged in there, so it'll be 2 plus 4, 6 times 4. Was there this one that it happens on? It's not this one. I forget where it is.
It would have a 1. So it'd be 0.
No, a negative 2, guys. So it'll be 2 minus 2 times negative 2. It'll be 2 plus 4.
That's
That's a y. That's right. So 2 minus 2, 0. All right. 2 minus 2 is 0. Yeah, all right.
It comes up to negative 16.
And then minus, that'll be 4 squared, 16. Yeah, so that's less than 0.
It's a
Saddle point. And then D21 should also be a saddle point. Let's see. Yeah, because 1 and 1 are both going to make that 0. And 0, 0. So where am I thinking about? In the homework somewhere, didn't I get a sign? I'm hoping I signed one where D was 0.
Yeah.
Just to let you see that happen.
So what does that mean?
Well, it's what you'd have to do. Let me see if you guys get this. There were situations where the secondary test clunked out at you in Math 180. I don't know if you guys remember this. But there were obvious ways to get to it. And there were a lot easier ways. You just had to look on either side of it. Go back to your number line that you had to make and see what it was around that point, right? So here you do the same thing, but you would create a little, here's your critical point, you create a little circle around it and check points around it to see if they're always less than or always greater than that. And you really just have to do it in certain directions from it. So there are other tests you can apply if this one is inconclusive. We just didn't take that step to talk about what those would be and why they would work, right? It seems like you'd have to check every point around that point, but you don't, because of the way that the gradient works, for example, from that point.
Are you going to give us something like that on the test?
You could definitely get something where D is 0, but you're just going to say inconclusive. Yeah, because that's as far as you know what to do.
I was like, oh, wow. So
Then you send it to the specialty center, right? So we're like this little normal hospital. We don't deal with those situations yet. Yeah, I don't think this book really got into what to do in those cases. So I didn't either. Yeah.
So would we say -2, 1 there is a saddle point as our answer.
Yeah, you'd say saddle point located at,
Okay, just making sure.
or saddle point at. I did 2, 1. I mean, if you give me the output, that makes a lot more sense for the min and the max, because then you're giving me a value for that min, a value for the max. But I don't necessarily directly ask for the value. Right? If it was an absolute max or min, then you have to find the value. Yeah.
I got one more question.
Yeah.
I'm just gonna grab the test. From 15.3, and it's, John had brought it up in your office, sorry, 28.
Yeah.
It's the drill that goes into a sphere.
So I gave John a big hint on how to do this problem, number 28 in 15. This is that problem, the type of problem where if I don't get questions on it, I know everybody's basically skipping it. And this is a problem that's hard to blame you too much for skipping it. It seems very difficult, and it actually is, but it gets easier if you look at it from all directions. So you start with a sphere. That's how you make sure people know it's a sphere. With radius R2. And you come at it with what I'm assuming to be, I don't think it says in the problem, cylinder, yeah, they don't say, of a smaller radius is what you'd have to assume. Otherwise you're just, eating the whole sphere away. Of radius R1. And you're going to drill a hole through the center. So if I look at it from this direction, which is the way people sometimes skip, because I know what's going to happen if I look at it from like this way, after I drill through it, it's going to look like that. Where this, and this is a very classic image, right? Where this is R2, and here's R1. I like it. But it's much more informative to look at it from this direction. What's it going to look like after I drill through it here? I mean, the weird thing about a cylinder is if I look at the results of what I've done from this direction, it actually creates a rectangle in the center. You guys see that? If I drill through this with this, so if I come at it with this, drill, that's going to go away, right? I've drilled through it. It's still connected, of course, right? But it's hard to draw that. You guys with me? It still has this kind of over here, right? So I'm sort of like, it's clear, maybe, this thing I'm going through. So I can see that inner missing piece. Let me stop here for a second. This is the slice of what's happening that people don't do. This is what the traces force you to do. The traces force you to look at something from all directions, right? So you can really get a clear idea. Here, people kind of stop here and like, what the shit do I do from here? But if I turn this, that's what it kind of looks like, right? Maybe. So what I'm trying to do now is determine the volume of the remaining bits, right? Okay, so, I don't know. I don't think many people got this far, even, to realize that looking at it like this is going to help. Now, let me say this too. Or don't you have a lot of problems where you have the idea is finding the volume inside a cylinder, but under this, between these two planes, we just did one like that, right? So wouldn't this be the volume that's outside this cylinder, but inside this sphere? That's another way to look at it. If I word it like that, it feels more like the problems. Some of them were like 7 through 14. I can't remember, 15 through 18. That wording kind of reformats it from like trying to imagine what this is going to look like, and then you're to the point where I'm going to just buy a bowling ball, drill through it with some and just look at the damn thing. You don't have to do that. You can actually rely on the mathematics itself. So if I say it like that, let me write it. So it's got to be outside the cylinder, inside the sphere. Now come up with the equations for both of those. How do you find the equation of a cylinder? And another part of this kind of problem that's really difficult for students is there's no set coordinate system here, which you have to kind of go, oh, good, I can just put the coordinate system however the shit I want to, right? So if I want to put it like this, right, in the middle of the Death Star there, or the Battlestar Galactica thing, whatever. And so this will be like, let me see how it says. So totally up to you, but this could be my x, y, z. So what would the equation of that cylinder be? You could figure that out. This circle will be sitting in what plane? XZ plane. I like it. And so which variable, of course, is going to be missing because that's the axis that's running along. Y is going to be missing. So what's the equation of that cylinder? X squared plus y squared. X squared plus z squared equals R1 squared. All right, we have an equation now. This is starting to sound and look a lot like the problems that I had earlier. What's the equation of the sphere? Equals?
R squared, or R sub 2 squared.
So it's got to be the volume that is outside of the cylinder, but inside this sphere, right? So I've recast the question into something less physical so that because I'm never going to be able to draw the image well enough, or maybe I can, right? And recast it more in something just pure mathematical, pure equation. So let me see. And I mean, this drill is not infinite in length, but as far as this sphere knows, it is. I just want to explain why I'm allowed to make the equation this when it's this finite drill, right? But as far as the sphere is concerned, it's freaking infinite. It went all the way through it. Okay, maybe. I don't know if anybody had a problem with that. So, for the way I formulated this, can't I solve both of those for z, or do I want to transform it over to polar? Now you see why this is sitting in polar coordinates section, right? So another way to do this, and this sounds like it's not that different, but you're used to having problems with this. They find the volume inside the cylinder, right? And under this. So you can do that first and then just subtract the volume of the sphere minus what you just found. You can just drill it out mathematically, right? You can do the volume of the sphere minus the piece I cut out. Okay, so there's multiple ways to look at this. For some reason, I feel like you guys haven't really tried this problem yet. I have this sense, right? And it doesn't, I just need to explain something. I'm not going to do the homework for you. That defeats the purpose, obviously, right? With that said, I'm definitely going to help you on the homework, obviously. This problem should have come up before now, so you would have had even more chance to have it done by today and show me and say, does this look right? Which is something you can always do. I've got all the freaking answers. I can tell you very quickly if it's going to be right or not. Yeah.
Should the answer have a negative value in it? Probably not, right?
Should the answer be negative? No.
That sucks.
Now, on the other hand, if this is the only problem giving you trouble, then continue working on it. But if this is not the only problem giving you trouble, let it go for right now. Right? I mean, I could put something like this on the test, but more than likely I'm not going to do something quite exactly like this. This is definitely one that's, you're forced to recast the problem in a couple different ways. You're forced to graph it in a couple different ways. You're forced to think about what the equations are going to be. And we're not used to doing that. We're not used to having no coordinate system set up for us. No equation given to us. We're not used to that. So this problem is not cookie cutter problem. It's okay. All right, I'm going to let you guys think about it. We'll come back to it before you leave. Anything else that you want to talk about from homework or the quiz? Yeah.
Just applications. With moment of inertia, when you try to calculate the triple integral, you have to think about what kind of a solid you have, right?
Are you looking at 15.4?
15.6.
15.6, okay.
Some examples, like after example 5. Like,
Oh, number 5? Exercise 5?
After 5. Then you talk about the moment of inertia.
Oh, yeah, yeah. Yeah, and?
And to calculate it, you just have to think about what kind of an object you have. Like if it's a sphere, you just have to think about the equation to start integrating it.
So, the shape of the object is going to determine what your limits are going to be, right? They have to give you the density function, which is going to be the inside. Your limits are going to be determined by what the shape itself is, if that's what you're asking. Right? So they have to give you the density function. The shape of the object is going to determine what the limits are going to be, just like we have happening here. So this one's a pure volume problem, but I could throw in here like find the density of this, and so I'd have to give you the density to throw in there. So that's just one extra thing. It's the same problem as, maybe not something like this, but it's the same problem as finding the volume between two surfaces or whatever, and just throwing an actual function in the middle. So you have to have 3 intervals then, right? Because it's a different density at every point, x, y, z. I don't know if that answers your question entirely. So it's not a different process. It's the same process. I just desperately have to have that 3rd interval because it's not going to be 1 on the inside now. It's going to be the density function, which has x, y, z as inputs. So it's different at every point in 3 space. Okay. Cool. Yes, ma'am.
15.6 or 16?
Oh, okay. Let's keep this here. Number 16 gives you this here. I tell you, this region is the tetrahedron with vertices 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1. So if you don't still have your isometric graph paper for some of these, it's a little crazy. But here I can get a decent feel for this. Doesn't have to be anything too perfect, so it's got to be 0, 0, 0. 1, 0, 1, so it's going to have to be up here. 0, 1, 1, so 0, 1, 1. And then 0, 0, 1, so it's going to have to be up here. So that's kind of nifty. It's got this going on there. Pretty freakadelic. And they do sort of a problem, an easier example of this, back on page 1075. And they say, where's this, blah, blah, blah. So, how do I say this? When you see a tetrahedron, so for example, this one here, do I want to throw this up there? to give you this example, number 5. So I'm given, without graphing all of this stuff, given those 4 points. 3 of them make this triangular shape here. Example number 5. So that's going to be in the YZ plane on this example. Then you have this 4th point that's not coplanar. That sort of defines the base of this thing. So the first thing you have to figure out is, now of course, these 3 points are coplanar. These 3 points are coplanar. These 3 points are coplanar. So this idea of coplanar seems to be important, right? So this tetrahedron is bounded by these 3 planes, right? So here, what I've drawn, it's not immediately useful. If they were all in the same plane, it wouldn't be a tetrahedron. It wouldn't be a solid. It'd just be a sheet. That would be no good. So notice how, for example, let's just look at Z at 1, and it goes through 0, 0. And then I've got this point here, which was, let's see, 0, 1, 1. So that's going to be, if I look at the Y, Z like this, just to give myself a better, so it's going to be 1, 1. So that's all in the YZ plane. Let me stop here. The most important part of a triple integral problem is what I said in the beginning. The part where people make the most mistakes is figuring out what plane your region's going to live in. Because then also at the same time that determines the surfaces you're talking about. So right now it looks like the first thing I noticed was that point and that point are really nice points. And then I could have picked either one of these, and I just picked that, just, flip the coin in my head, whatever. Right? So what's happening here is these 3 are kind of like that back wall of this tetrahedron. And this point, what would that be? 0, 1, 1. So that's coming out here, 0, 1, 1. That point here, that's what makes this a solid shape. Let me stop there for a second. So really what this boils down to is finding the equations of the planes that are above this region. If you want to use this region as your input region. So if you look back at example 5, why did they choose the XY plane? If they tried to choose some other plane, something really, really sucks about it. Let's see. Put the booklets out there. So if you have a book, it's page 1075. Okay, now. So right here, you see how they chose the XY plane to be their input plane, right, where their region lives. The inner one is the one between the surfaces you're talking about. Notice how do I want to say this? If I used the YZ plane, well, could I try to use the YZ plane? Then I would have this region here in the YZ plane. This back triangle would be my input region. So I could set up the same way. But they chose to do XY plane. Now, why do you think they might have done that? What's the part of this that, if I chose the YZ plane, is Z going from a single surface to a single surface? No, it's not, right? But if I choose, so here, if I choose this to be my input region, then aren't all of these going to this plane? That's why they only need that single plane to define what's going on. Do they have to worry about this side? No. Right? I sort of, that input region had that kink in it already. So that's where it showed up. That just changed my X and Y limits. I really want you guys. So what sucks? For double integrals. Remember when we first started talking about them, we had a couple that had to write 2 intervals for. 2 double integrals. Why did that happen? Because somewhere the function changed. All right. So that kink happened, right? So what I'm trying to show you is you have a lot of options. In fact, there's problems that tell you to write it all 6 different ways. And I bet that's some of your favorites if you try them out. Yeah, it's sarcasm, sarcasm. That's why it's so important to figure out from the beginning, which way am I going to do it so I don't have to write multiple double intervals, right? So if I try that YZ plane to be my, my input region, Z would go from 0 to 2 different planes. So I've got to figure out, I could use the YZ, but where's that, I got to figure out where's that going to go to. Is there a single plane that kind of is hovering over that, or is there 2? What's it look like in the XZ? Is it in the XZ? Yeah, so if I did XZ, so I got 0, 0. I got 1, 1. Right? Because this 0 would mean it's in the XZ plane. Are you guys seeing what's happening? And then I've got 0, 1. So it looks the same. In the XZ plane, that triangle, that wall that's in that plane, it looks the same. Maybe you guys are getting it. And then I could try the last one I haven't tried yet, the XY plane. See what it looks like in the XY plane. It's gonna. What would the projection look like in the XY plane? Right? I could look at that. That to me is going to be the one that's possibly the best. I don't want to erase that. So this one, these 3, let's see, where am I at? Yeah, this was, yeah, there it is. So that's in that YZ plane. These are in that XZ plane. So let's see, how do I want to... I just need a better image of this. I mean, it's easier to see, obviously, here, which one's going to be the better one to pick. Let's see. So that one extra point there. I mean, this is what's missing. The only thing missing is that. Ugh. Oh, all right. So, for example, how could I figure out the equation of the plane going through any of these 3 points? Through any 3 points? So, for example, what about the 3 points? Let me see. What's the best points to pick there? I think I still want to look at the XY projection. What's that going to look like? looks right. I need some better graph paper. I can't really. Wish I had some isometric whiteboard paper. That would be awesome. So see, this is definitely there. This is definitely here.
You want to borrow some isometric paper?
Yeah. Thank you.
I got you.
All right. Let's start.
Oh no, sacrifice my paper.
Let's see.
Just
I need a decent pen. Okay. So let's take a look here. Let's make a decent scale. We can play around with stuff a little bit. So I've got. Right. Let's go by 1/2 here. So I've got the point 0, 0, 0. No problem there. I've got the point, where'd it go? 1, 0, 1. So 1, 0, 1. So that's in this XE plate. 0, 1, 1. 0, 1, 1. So those 2 points that are there, they're kind of like up towards us, right? And then 0, 0, 1 kind of completes it. And I forgot I was going to do double scale, didn't I? Oh, would have been a smart idea. So 0, 0, 1 is going to be right up there. So here's that, in this plane, here's that triangle I drew just a second. Here's that other triangle I drew just a second ago, right? And then I've got this guy. Whoop. I should have blown this up a little bit. So I'm going to blow this up a little bit. Let's go by 2s. So I've got 0, 0, 0, 1, 2. And I've got, so let's see, what was it? It was 1, 0, 1. So 1, 0. So 1, 0, 1. And I've got 0, 1, 1. So 0, 1, 1. All right, so this guy lives in this plane. This guy lives in the YZ plane. So that corresponds to those traces we just drew. Right? And then I've got these vertices connected. Okay, so now I've got this triangle here. And, all right, now this is what I need. Okay. So notice how, to get this entire, so this here, so it's kind of coming out at us, and it's got that seam right here. You guys see that? So I've got this flat side here, I've got this flat side here. I've got the top here, that's the part that was difficult to really kind of get at. And I've got this that's coming straight up. Now, the way it looks to me, I really want you guys to see this. The idea for a triple integral is if I can identify two surfaces that my z or whatever variable goes from to. So for example, it goes from this bottom plane to this top plane. And then my input region would then be xy. So that's, once you figure out either which variable is defining your surfaces that you're going between, or you define which variables make an easier input plane region, that sets up the entire thing. Now what's left over for us to do is, this plane is easy. The definition of this plane, please let that be easy. Those points, what's true about those 3 points? Those 3 points, what's true about all 3 of these points?
Z equals 1.
There's the equation of the plane. All right, I like it. So where does z start? It starts on this plane. So now it boils down to, can you figure out the equation of this plane? Now I've just drawn the triangular piece, but you understand there's a plane there, and I'm just worried about the part that's right there. Then I can project this into the xy plane and figure out what my x and y limits are going to be. So far it looks like, let me catch that for the people at home. There's that beautiful thing there. It's gruesome. Okay. But the part, I really want you guys to see the part that was, for some reason it was just really hard for me. I couldn't think about it mathematically. The z equals 1. was getting a hold of this guy and figuring out what this guy was going to look like. But what really, really mattered was, it's easy to find all the equations of all these planes. Because obviously this plane, what would the equation of this plane here be? What plane does it live in? So that's y equals 0, right? So I could go y equals 0, 2, but do you see how the y's would go to two different? Okay, that's the part that's not easy to see on this disgusting thing I've drawn, but it's easy to see in that computer-generated one in the book. I want to pick it so I don't have to set up. Now, if you don't care about setting up two double integrals, no problem. But you have to figure out, because I'm going to have to figure out two plane equations anyway. Well, one of them's easy, z equals 1. How do you figure out the equation for this? What are these 3 points? These 3 points, of course, are all the points that are not 0, 0, 1. Right? So those 3 points are here. So what's it going from? I know it's going to z equals 1. What's it going from? What's the underneath plane? What's this plane jutting up? Well, I got to figure out the equation of the plane that goes through those 3 points, right? And that sounds like stuff we've done before, and they're relatively easy points. So it's going to be I know this is going to be 1. Oh, just to find the volume. That's going to be 1 inside. And then I got to figure out my XY stuff. I got to figure out the equation of this plane here, the plane that goes through those 3 points. The example they gave was a simpler example. But this one you can still, how do I figure out the equation of the plane? What did I just do? I picked the wrong 3 points. All the points that are not this. So what's really, really nice about this, since it has to go through 0, 0, 0, what's it got to look like? All right, so what's a plane look like? What's the equation of a plane? The most general equation of a plane. Okay. So it's got to go through the point 0, 0, 0, which means it cannot have a line or like an equivalent of a b or something, right? So it's got to be ax plus by plus cz equals 0, because I could just put 0, 0, 0 in for that. So then it just becomes determining what a, b, and c are. And you have a few different ways you can do that. You can do that non-vectorially, or you can just attack it with cross product, figure out the normal. All right, make your vectors in between there. So, all right. So this is a nice callback problem to how to develop the equation of a plane, because the surfaces that this thing lives between are planes. And I need their equations so I can actually plug them into the limits. So I got to determine the equation of the plane in that lower plane. So, how do you get A, B, and C? What's really, really nice, since there's 0, 0, 0, these are like vectors. Right? So then you can just cross those. And that would give you the components of that vector would be the normal vector, that would be A, B, and C. You plug that in here. Now, in the XY plane, it's going to be this projected down, right? You guys see that? So, let me ask this to get a little more directly. Do you guys see that? The two surfaces. This surface, this lower one, is that cool? You guys, it's like a plane like this, right? And this surface, the top. So I got a plane coming like this, and it meets this other plane on the top, like that. That's what this is. So that's coming out at you like this. Okay. So I need to find the area in my input plane that actually has outputs to be all the points on those two planes. So it's just going to be this guy pushed into the XY plane. Say this again. There's a problem I really love that has the intersection of two paraboloids. And they're somewhere off out that way, right? Stay with me. I can't remember if my signs went. So the thing that freaks people out is they're not sure what region they're talking about to actually develop for their input region. But it's going to be what points actually lead to all the points on these surfaces is this projected down. This is the widest part of this whole thing. So what inputs lead to this output? Something in here. The intersection of these two is where it's going to be, and I push it down. In fact, that very first image I showed you had that red region that was just the projection of the actual widest part of it. So what I've got here is the same idea. This is all the points here. That's the furthest out the points get. That is going to be my region of integration. I just have to push it down into the XY plane. So this region here, what is the region truly, technically? It's the region that has all the outputs from its inputs and nothing else. So if I push this triangle down into the XY plane, this is my region of integration. Because it has all the points I need on this surface, and it has all the points I need on that surface. That's it. That's all I'm saying. So this problem is a classic problem. This, if I push it down here, it would be a region that has all these outputs, all these as outputs, and it has all these as outputs also. Nothing's missed. And it doesn't have more than it needs to. So that's the region that I would integrate across. So there, all I have to do there is figure out what the equation of this line is. Yeah, there you go. Sweet. Y equals 1 minus x. Cool. So, what do I have? I have, once I get the equation of this plane, I would put it right here. Blah. The equation of this plane, I'll put it right there. Then I've got x going from 0 to 1. So I'll make this outer one x. X goes from 0 to 1. As y goes from... Yeah, so x goes from 0 to 1. As y goes from 0 to 1 minus x. So all you need now is just the equation of that plane, that bottom lip of this thing. Right, there's a mouth. I thought they gave you, I guess they will not. No. Okay. Oh, this one was easier because they actually gave you the equations of the planes right at the beginning. This one just gave you the vertices. That's why this one's a lot more, or a bit more work. Okay. Anything else from practice test, homework, quiz? Which one was that? Still need that, yeah.
Can you go over 36 on 15.3?
Oh, yeah.
And I gotta start by keep coming up with the wrong answer. question.
All right, so you got some sprinkler. Okay, so the distance of our feet from the sprinkler. So if you're right at the sprinkler, it delivers 1 foot per hour. That's crazy, right? And then it drops off from there.
It's inverse R.
Yeah. And normally, actually, it normally has like, it delivers the most
Out.
here, and then kind of like a little bit of spritzing down. Yeah. Anyway, so they've made this weird new sprinkler for some reason. And it's not even allowed to equal 0, so okay, I feel a little bit better. What's the total amount of water supply? Okay. So we got a flow rate, feet per hour. And we want to figure out the total amount per hour. Yeah, okay, cool. So it's a radius 100 feet, so it goes 0 to 100. E to the negative r is our flow rate. It's going to be the, where's that going to go?
That's our.
Inside. I like it.
Here's this already.
Yeah. So let's see, what's the total amount of water supply per hour to the region inside the circular radius? So I've got this region, and I've got it well defined for myself. I know this is going to be the inside. This is going to be the like in this case, the flow rate. So it could be a density function, which is itself a rate of distribution of mass, right? So the inner thing is a rate because we're integrating it to undo the rate part. You just get an amount. And of course, this is going to be RD theta. And so what's R going to go from to? 0 to 100. And theta is going to go from 0 to 2 pi because it does make a circular pattern. It doesn't skip some of this out. Hopefully it's working correctly. Blah, 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 blah. Let me see. I don't see anything too freaky about this. This is why I told you it looked like it would be relatively simple to look like. Let's see. Yeah. You guys see how that gets put together? So there's a function that determines a flow rate, some kind of a rate. And that's really what density is. It's a rate. I've got a really well-defined region. You can't beat this shit. I mean, I didn't have to try to do some weird stuff to figure out what this was. They basically told me what it looked like, what its dimensions were. It's like, oh, thank God. So part A seems pretty simple. What do you guys, how do you do this? That's the part that's more interesting. Maybe that's why they give it to you. Make sure you get some more stuff like this. What do you have to use for the inside? By parts. I love it. Yeah. So you just got to do that by parts. And real quick, just make sure everybody remembers how by parts works, just in case some teacher puts it on some tests in your future. What would you let you? So what do you have to identify? U and dV. I like it. You got to identify U and you got to identify dV. I don't know which way you guys were taught to set it up, but oh well. U's normally we'd let U be the polynomial piece, because when we do du, it's basically gone. Then dv's got to be the other piece. Yeah, I like it. So the integral of, so we're just worried about the inner one, right? Just make sure you guys understand. The outer one is going to be nice and easy. In fact, I mean, the book even shows you that I can just look at this, the product. When there's no mixing of variables, there's no mixing in any of these functions, you can just actually separate them as a product. Which is a little bit weird, but not really. Integral of u dv equals uv minus the integral of v du. I like it. I don't think I've ever heard any songs for that one. So the inner piece becomes integral of v du, so that's got a negative on it, so plus e negative r dr. That became much nicer, right? And from 0 to 100, and this has got to be from 0 to 100. You'll get a whole bunch of, minuscule e pieces and stuff like that, right? That's easy. Plug stuff in, and then you're going to multiply that by 2 pi. Is that good for part A? All right. Part B, is part B weird? The average amount of water per hour per square foot. Oh, come on. Supplied to the region inside the circle radius R. Well, what'd you try to do? Oh, for part A?
Yeah.
And this is what you did? All right.
I've got the same setup as you, everything.
So let's see, you get negative 100 e to negative 100 plus 0 plus, so this will be negative e to the negative r. Right, for the integral there? So it'll be negative 100 e to negative 100. Let's see. So that'll be minus e to the negative 100 plus 1. I mean, at least that's positive. I'm really sure that e to the negative 100, I don't give it a multiply by 100, is still way smaller than 1. So, is that the answer you got? Or? All right. And then how do you do part B? Did anybody get part B? Is that? We know the total amount of water supplied per hour. So now I just want to know the average per hour per square foot. So I just have to know the. Here's my region. Yeah, just got to know the area of my region, right? And then divide by it. Oh, I think you guys expect that to be that one. That problem is actually kind of a little too nice. The reason that problem is mean is because it's too nice and you make too much out of it. I think. I don't blame you too much. It's number 36. Normally that's where they get really freaky, but that was really straightforward, surprisingly.